So, yeah, the homework is after lab today. Monday, people are a little bit behind everybody else. Monday, we did the first thermo lab today. After today's lab, I think the homework is due either tonight or tomorrow night for the first part of chapter 5. Is it tomorrow night? Tonight. Okay, so after today's lecture and today's lab, Monday, people, you all should be caught up, and everybody should be able to do the first part of chapter 5 homework with a little input on your own. All right. Physicists and chemists sometimes classify energy in a little bit different ways. This is sort of like overall classification of the types of energy that most physicists or engineers like to classify things into. They do also talk about transition between one form of energy to another. And the overriding big picture idea is what we call the first law of thermodynamics. Does everybody know the first law of thermodynamics? Energy cannot be created or destroyed. The amount of energy into one system, if it's transferred into another system, is the same amount of energy, it's just in a different form. Okay? We use a particular unit to describe energy, and the units of energy are very similar in that they are packets. I want you to think of energy as a finite packet. When people think about energy, you turn on the faucet and some energy starts coming out, and it's this long stream. Well, no, energy is in packets, and we describe the packets of energy using different words depending on what kind of energy we're describing. For example, light energy, the packet we talk about, is a photon. Right? A photon is a packet of light energy. Einstein talked about the duality of the nature of light, that it travels in this packet of energy, but it also travels in wave nature. Okay, so that's light energy. Does anybody know the unit that we talk about for heat energy? Joule is in the English unit. What is that unit in, excuse me, Joule is the metric unit. What is that in English units? Calorie. Okay, and it turns out that there is an equivalency between calories and joules, that 1 calorie is equal to 4.18 joules. Right? That's like 1 inch is equal to 2.54 centimeters, right? Okay, so this is the English unit. This is the metric unit. So I want you to think about energy in terms of these finite little packets that we can move from one place to another. And this idea of thermodynamics is we're studying energy and how it moves from one place to another. Physicists like to define energy in terms of its ability to do work, and chemists use energy as a description of work only in a very narrowly defined type of situation, and that situation is where you have a closed container. In chemistry, the only time we're able to do work, and the definition of work is that you have to move something. Right? So physicists like to use work because everything in physics is work, right? You're moving a tractor up a hill, there's work involved. You drop something and it falls to the ground, there's work involved. You throw something and it travels in an arc, there's work involved. So if I'm a physicist and I lean up against this wall, am I doing any work? By this definition of the physicist. No, because the wall's not moving, right? So in chemistry, the only time we really define energy as related to work is when we have a closed container that has perhaps a gas in it. And the gas is reacting somehow to expand or contract, and as its ability to expand or contract changes, then it is not able to do work, right? So we have a closed container, and it is able to expand, then the front of the container will move out like a piston in a car, right? You explode some gas in a piston, it moves it out, and it turns on the flywheel that moves the engine on your car. All right, so in chemistry, really the only time we talk about work is in a closed system. The majority of the time in chemistry, we do our experiments in open containers, right? So you're putting stuff together, and you're measuring changes in open containers, so work is not easily measured in chemistry. So we tend to not really involve our definition so much in work as we do in what we call Q. Okay, Q is what we're going to talk about in terms of heat in this whole chapter and beyond. And Q is heat. Now, how could we define heat? Heat is energy, absolutely. Heat is definitely energy. How can we measure heat? How do we measure heat? Changing temperature is only part of it. What does temperature measure? Let's step back and think about temperature. What does temperature measure? Okay, temperature measures the average speed of the particles. Right? So just like the scores in this class are on what we call Gaussian distribution, units in energy or temperature is also distributed Gaussian and Gaussian distribution. Let's see, where is my, oh, I missed it. There we go. Okay. Gaussian distribution, if you recall, looks, it's worse. Okay. 10% on each end, 20% from there, and 40% in the middle, right? Okay, so if we take the temperature of a substance, there's my thermometer. I'm taking the temperature of a substance, I'm looking at the average speed of the molecules at that point. Say it was 23 degrees Celsius was the temperature that I measured. Well, there's some molecules that are moving a lot faster. They might even be moving fast enough to escape the liquid. If I take a container, an open-air container, and I set it out in this room, is some of that liquid going to evaporate? Yes. Did the water boil? No. But there were some of those particles that changed from a liquid to a gas while the container was sitting there, right? So they must have had, the ones that were able to escape, must have had more energy than the rest of their peers that I measured their temperature of, right? It's like if I measured the height of everybody in this classroom. I said, all right, everybody who plays basketball or volleyball now has to leave. And then I measured the height of everybody after the basketball and volleyball players left. How would our average change? The average would go down, right? Because basketball and volleyball players are generally the taller people in the group. So when you take out the fastest moving particles in a process like evaporation, the average of everything else changes more towards the lower end of the scale, right? So we have some particles that are moving really, really slowly in our average, but the majority of them, when we measure the temperature, are moving at what we call this 23 degrees Celsius value. So if we talk about Q being energy, and we measure Q in these units of energy we call joules, or we're more used to sometimes calories because we have to count calories, there's certain things that depend on how much energy can be transferred. Here's a good example. Say I have a cup of water versus a swimming pool of water. A cup of water and a swimming pool. They both have water in them, and the water I measured is still 23 degrees Celsius. Which one of those is going to have more energy? The swimming pool. That's fairly easy to understand, right? So the amount of energy that can be transferred is certainly dependent upon the mass, right? Let's use that as our first part of our equation, mass in grams. And certainly the swimming pool versus the cup, the swimming pool would have way more energy because there's more mass. And each of those particles in liquid state possesses some packets of energy that they're holding on to that causes them to move in a certain way. All right, so let's go back to our analogy of the cup and the swimming pool. Now I have 2 gallons of boiling water. And we're in Mesa, or Chandler, so it's about 98 degrees Celsius boiling water, right? I got 2 gallons of boiling water. I'm going to pour this gallon in here, and I'm going to pour this gallon into my swimming pool. Which one of those bodies of water, the cup or the swimming pool, will have a greater change in temperature after the addition of a gallon of boiling water? The cup's going to have a lot larger change in temperature. So certainly the amount of energy that can be transferred depends on the change in temperature, but that's not the only measure of heat energy. Let's go back to a new metaphor. Say, for example, now I have 2 cups. They're both at 23 degrees Celsius. They both have the same volume in them, but one is water and the other is milk. I take 10 mils of hot water, and I add 10 mils of hot water to the milk, and I add 10 mils of hot water to the water. I'm not going to ask you to determine which one would have a larger change in temperature, but do you think there would be a difference? Absolutely. Why do you think there would be a difference in the change in temperature between the water and the milk? They're both liquids. They're made of different stuff. Right? The molecules inside of them are going to be able to move faster or slower depending on a whole lot of different variables. And that particular characteristic of a substance we call the specific heat capacity. And the units of specific heat capacity are derived units. They are joules per grams degrees Celsius. Those are the units of specific heat capacity, which are joules per grams degrees Celsius. Now, is that better? Oh, there we go. I like that much better. Okay, so joules per grams degrees Celsius. Now, I want you to think of energy like money. If you're paying bills at home, you pay the power bill, you pay the light bill, you pay for gas or whatever you pay for, you know that energy costs you money, right? So think about it as cents, or how much it's going to cost you in energy to raise the temperature of 1 gram of a substance by 1 degree Celsius. That's what we call the specific heat capacity. If you take out the table that I provided to you in class today, this is a table of heat capacities. We have 2 units. We have little CP and big CP. Little CP is specific heat capacity, and big CP is what we call molar heat capacity. Specific heat capacity versus molar heat capacity. All right, so the ability of an element or a substance to absorb heat energy is very dependent on what it's made of. Let's look at things that we could compare that are fair. It wouldn't be fair to compare, say, a solid to a liquid, right? In terms of its heat capacity? Let's think about that. Let's think about solid, liquid, or gas comparisons and what's available and easy to compare. All right, so if we said we had solid to liquid to gas, those are changes. Solid to liquid, we call it melting, right? Liquid to gas, we call it vaporization. Gas back to liquid, we call condensation. And liquid back to solid, we call fusion or freezing. So they're processes. In this direction, we have to put energy in, right? If we're saying that this is our system, the change from solid to liquid to gas, and the surroundings are everything outside, then the system requires energy to go in this direction, right? To go from solid to liquid, you have to put some energy in to melt that ice. To go from liquid to gas, you have to put some energy in to vaporize that liquid. Conversely, when liquid changes into solid, energy comes out of the system and goes into the surroundings in this direction. So in that direction, we have energy out of the system. So I'm describing this whole idea as the system. Well, that's because of the way things move. If I took and compared time in minutes to temperature in degrees Celsius in this axis, and I looked at the way temperature changes as time goes on. If I started with a beaker of ice, okay, and I froze my thermometer in a beaker of ice, it was embedded, I set the whole unit into the freezer, right? So I got a beaker that's in the freezer, and it's got ice frozen around a thermometer. Well, what temperature does ice melt at, or what temperature does it start to melt at? 0 degrees Celsius. All right, so we're going to use Celsius here. 0 degrees Celsius. At sea level, what temperature does the water begin to boil at? 100 degrees Celsius. Okay. So here's where we start. Here's our time 0, right? Before I put it on a hot plate. So I took the temperature of my ice, and it's some value below 0. People don't realize sometimes they think ice is always at 0 degrees. No, ice gets much colder than 0. it actually just begins to melt when it hits zero. So when you have ice in the freezer and a thermometer embedded in it, the ice would be much colder than 0 degrees Celsius. So I would take my beaker of ice that had the thermometer embedded in it, I'd put it on a hot plate. I'm going to set my hot plate to high, right? So my ice would begin to warm up until it got to 0 degrees. Once it got to 0 degrees, the temperature would go up and down. This is where the ice begins to melt. At 0 degrees, the temperature would go up and down until what happened? The temperature wouldn't go up measurably again until something happened to the ice. All the ice melted. At this point here, all ice is melted. Then the temperature can go up. Well, I didn't change the hot plate setting. During this particular change, where did the energy go that the hot plate was adding to the ice? It went into what? It went into the ice, but what specifically? If I was a molecule and I was at my solid state, what kind of movement can I have as a molecule in solid state? Vibration. I can always vibrate around a fixed point, right? So as I add heat energy to the ice, what's going to happen to the level of vibration? It's going to increase. It's going to vibrate more and more and more until what happens? They break the structure of the crystal, right? They're no longer a solid. Now they vibrate and they rotate. So you actually, that transition between solid to liquid to gas, solid has only vibrational motion associated with it. Solid is only vibrational motion. As I add heat energy, I heat it up and heat it up, it starts now accepting vibrational plus rotational motion. So liquids vibrate, each particle of liquid will vibrate, but then it also rotates. So you've got liquid molecules that are vibrating and rotating as they're moving around. So now it has that second mode of motion. That energy that was added went and was stored as what we call potential energy. So physicists like to further subdivide things into two types of energy: kinetic energy and potential energy. All right, kinetic energy we can define as the energy of motion. Okay, particles moving. Temperature. Temperature is also sometimes defined as the average kinetic energy of the particles, right? So if we're measuring the average motion, we're also measuring the average kinetic energy of the particles. Potential energy is stored energy. In this scenario, we're adding energy, but the energy that went in this section here that was being added, this was being added as kinetic energy, right? Because the molecules were moving faster. Here, the kinetic energy didn't change. The ice at 0 degrees and the liquid water at 0 degrees were the same temperature. But the liquid water had more energy associated with it because it had stored some of that energy as potential energy in the energy of motion, that additional mode of motion that it was able to receive now causes, even though the ice and the water are at 0 degrees, the liquid water has more energy because it has that additional mode of energy, and it didn't change the temperature. It simply changed the way the molecule was moving. All right, so let's go back and think about liquids. Now we've got vibrational and rotational energy. It heats up even more. We looked at our measurement here. It would heat up and heat up and heat up until it got to this point. And what would this point be right here? That's where it's boiling, right? And then the temperature would never get hotter as long as we had an open container. It would never go above 100 degrees if you're at sea level, as long as the container is open. So where's all that energy going that I'm adding here? Because I'm still keeping it on the hot plate. Where's all that energy going? You have an additional mode of motion as a gas. What's that third mode of motion? Called translational. So gases have vibrational plus rotational plus translational energy, meaning they can move from one place to another, a linear distance, because they're free in the air. So gas particles are vibrating, they're rotating, and they're translating from one place to another. So there's where the second bit of potential energy is being added in that third mode of motion in the molecules. So if we go back and compare specific heat capacities, and we want to make a fair comparison, we want to compare solids to solids, liquids to liquids, and gases to gases, right? Because that would be fair because the modes of motion change. So let's compare metals in our little CP, actually it's little CP, big CP, and the molar mass. All right, so I'm going to ask you guys to call out these values to me, and I want to use the three metals that we used in lab. Okay, let's see, in lab we used iron, we used copper. Actually, you know what, I'm going to put copper, the lightest one first. Let's use aluminum is up here. We use aluminum, and we use iron, and we use copper in the lab. Those are the three metals that we use for the specific heat lab. All right, now I want you to look at that table that I gave you. What's the little CP, which is in joules per grams degrees Celsius? Big CP, which is joules per moles degrees Celsius. Whoopsie. What is the little CP for aluminum? 0.897. What's big CP for aluminum? Thank you. What is little CP for iron? 449. What's big CP for iron? Little CP for copper? And what's big CP for copper? All right, just as additional information, aluminum's molar mass, and what are the units of molar mass? Grams per mole. And how much does 6.02 times 10 to the 23rd particles weigh? Aluminum, it looks like the molar mass is about 27. I'm just going to round to whole numbers just to make it easy. Iron's molar mass looks like 59. Is that what I'm seeing from here? Okay, so 56. And then what's copper? 64, if we rounded it, approximately, right? All right. Well, let's look first at these values here. Those values are not changing significantly, right? There doesn't appear to be any sort of a trend between those, and the numbers are not significantly different. If we did a statistical analysis of these, we would see that the numbers are not significantly different. Why? Does it cost you the same amount of energy to change a mole of those by a degree Celsius? Why is that true? Why is that value so similar? Think of the units. Think about energy in terms of what it costs you. Energy is cost, right? Per mole degree Celsius. Yes?
Well, all of your metals that are close to each other are the density of the atoms are fairly significant.
Well, I like the first part statement that they are all metals and they're fairly close to each other on the periodic table, but there is enough of a difference in their masses to certainly make a difference in their density that would be significant. All right, what's the quantity here? The cost per mole. How many pieces am I talking about here? 1 mole, which is how many? 6.02 times 10 to the 23rd, right? Okay, so I have an equal number of pieces here. Let's think about molar mass idea. If I have 1 gram of each of these things, right? I'm going to make each box fairly much the same size, meaning I have 1 gram of each. Which one of those things is going to have the biggest atoms in it? The copper. The copper is going to be pretty darn big atoms, right? So you're going to be able to fit that many. All right. Is iron smaller than copper? It is. So would I have more or less atoms? I'd have more atoms in my gram, wouldn't I? Because if I can fit more in a gram because they're smaller, right? These are big atoms. These are smaller. I'm going to fit more. What about this one? Am I going to have more or less? Even more because they're smaller, right? All right. We just talked about energy being accepted by particles in terms of their motion. Since all 3 of these are solids, what is the only way that they can accept energy? The only type of vibration they can do? Vibration, right? They can only vibrate. That's the only kind of energy they can do. They can't store any energy. So So that's a fair comparison. Why is it that it costs a lot more money? If we looked at it in terms of money, right? Cost, how much energy it's going to take you to change 1 gram of that substance by 1 degree Celsius. It's going to cost me 89 cents to warm up a gram of aluminum. It's only going to cost me about 45 cents to warm up a gram of iron. It's only going to cost me about 39 cents to warm up a gram of copper. Why is that true? There's more atoms. Who has the most atoms? Aluminum. More atoms can vibrate more. More atoms can accept more energy because more atoms can accept energy to vibrate, right? It's like if I came into this class. I said, all right, I'm going to give everybody in this class a penny. I'm going to give you a penny because I'm a teacher. We're all in the penny, right? Okay, so give everybody in this class a penny. It will cost me about 50 cents. I go into lab. I want to give everybody a penny in lab. How much is it going to cost me there? A lot less, right? Like 20 or 25 cents maybe. And that's because there are fewer people in lab that have to give a packet of energy to. And if we think about energy as a penny or some exchange between one thing and another, I have to exchange a whole lot more energy for aluminum than I do for copper. Here's a good story that kind of goes along with this idea. You guys all know I have 2 sons, right? There has lots of stories. When they were both so my oldest was in high school, he was a band nerd. And my youngest, he was Mr. Sports, Mr. Baseball, football, that kind of stuff. Okay, so we used to go to the football games at Dawson High School to watch my oldest son in the halftime shows. And I only wanted to come and watch the halftime shows because I don't have much interest in football, although my youngest son really likes sports. So we would arrive usually sometime around the second quarter, and we'd sit down. And then the band would come on during halftime and watch the band, and I'd wait for everybody to come back into the stand and clear out. And sometime, middle of the third quarter, clubs went in or something, we'd go. He would get really upset because he wanted to stay and watch the football, right? You guys know how that is. All right, so he figured out that he got a really messy snack somewhere towards the end of the halftime that I'd make him sit in the stands and we stay a little longer so he could eat that messy snack and then have to bring it back. So he's a smart guy. This is going along with the work, right? All right, so we're in the stands, and it's a hot September evening, and so he goes down and he says, like a snow cone. And he brings the snow cone back up, and he's measuring on the snow cone. We'll have to have a conversation. And he goes, no, watch this. This is very odd. He goes, if some of the ice falls from the snow cone to the metal of the seats that we're sitting on, it melts really fast. And if some of that ice falls onto the metal that we're standing on, it melts really slow. He goes, why is that? So we had a great discussion of chemistry and particle science and specific heat capacity right here in the football stands. And here's one that was 12 years old and dad. All right? So here's the discussion. Which one? One of those things was made of aluminum, and one was made of iron. Was the seat that our booties were on the aluminum, which melted fast, or was the seat, the thing we were standing on the aluminum, which melted slow? Which was made of which? Which was the aluminum, which was the iron? The seat was the aluminum. Because not only does it take more energy to warm up aluminum, you have to think of this idea as specific heat capacity is sort of dual in nature. Not only is it going to cost you more energy to warm up aluminum, but energy is also moved more efficiently by aluminum. In this case, the ice fell on the aluminum. Was energy going from the ice into the aluminum? Where's the energy going? It's going from the air through the aluminum into the ice. So the aluminum makes a better conduit of energy because it has more particles. It can accept more energy, it can move more energy from one place to another because of those additional particles, each of which can accept a packet of energy and vibrate. You have fewer particles, like the iron. There's not as many particles, it doesn't make as much of a comparison. Here's another good story. I was thinking of, actually I'm going to this summer, remodel my bathroom in my bedroom. I love copper. Copper's my favorite metal. I was looking online for one of those big iron clawfoot bathtubs. It's like a nice big bathtub. You sit in so big. Alright, so I'm looking through online, I'm looking for clawfoot bathtubs, and no one applies like copper. I'm like, oh my gosh, that's beating rapidly. copper cloth bath. So exciting. It was like $3,000. I said, well, so much for the copper bathtub. Iron one was about, $5-6 grand less than the copper one was $3,000. I started reading the manufacturer specs on the copper one. They said in the specs that if you purchase the copper bathtub, it will keep your bath water warmer longer than the iron one would. And I'm wondering, is that true? Is that true? Are there, now they must have had some physicists or chemists on staff, right, to be able to make this claim, or maybe some engineers, because engineers like this whole capacity thing. Is that true about copper versus iron? Would the copper keep my bath water warmer longer? Yes, it would. Why? It's not as good of a conduit of energy transfer. It takes less to warm it up, right? It wouldn't take as much to warm up the copper. Okay, and one more cool demonstration. You guys are gonna like this. All right, touch the metal of your desk and the top of your desk, the plastic part. Which one feels colder? The metal feels colder. What if I told you they're exactly the same temperature? I would believe you not. Well, they are. They're exactly the same temperature, just like these two pieces of material up here. This is basically the same as the metal that your desk is made of, and this is basically the same as the top of your plastic is made of. If I take 2 ice cubes, and I put 1 ice cube on each of the platforms, this one feels colder. This is the one that feels colder. If I touch it, it feels colder. This one feels warmer. I can make that, there we go, a little better. It adjusts itself. Okay, you can see from the paper towel. Which one is melting quicker? The one on the left, but this is the one that feels colder. It's melting the ice faster, yet it feels colder. It feels like the metal does to your hand versus the plastic. So why does the one that feels colder melt the ice faster? It has more atoms in it, and it's able to move energy from one place to another. Okay, let me give you these questions here. Look at the paper that I gave you. This is a specific heat capacity. The questions on the back are fair game for a quiz on Wednesday or for your exam that you take a week from Wednesday. So they'll put you like these in your homework, but I'm giving them to you in advance so that you know what the questions are. Okay? You can think about them, look at the specific heat ideas, think about our discussion today.